Okay, looking at tangents today, first of all, an example, or to follow what the lesson is talking about here, draw a circle with a line that does not intersect it. When we do that, we have no intersection. Now, if I was to draw a circle with a line that intersected it twice, it would look like that, with its two intersections there. This is called a secant. A line that intersects a circle in two places. Now, what we're going to focus on today is a line that intersects a circle at exactly one point. This is a tangent line. As for a circle that has a line drawn through it 3 times, not possible. And if you'll read these notes to the left, you'll see what I'm talking about. You can't draw a circle with a straight line that intersects it 3 times. Can't be done. But today we're going to focus on this tangent. The relationship between a tangent, notice that if I was to draw the radius, does that line not look like it's perpendicular? In fact, it is. A line is tangent to a circle if and only if it is perpendicular to a radius. Goodness gracious, you know what I'm trying to say there. Radius there. Drawn to the point of tangency. Basically, the point where that line intersects the circle, if you draw a radius to that point, it will be perpendicular. This helps us looking at solving problems. For instance, here we have KL is a radius of circle K. Determine whether LM is tangent. Well, in order for us to know that, if it was a right angle, if this angle was a right angle, then we would say yes, it is tangent. Of course, we have no way of measuring that. However, we can use the Pythagorean theorem, because if this is a right triangle, then 20 squared plus 21 squared should equal 29 squared. So let's go ahead and solve that and see if that's the case. We end up with 400 plus 441, which is 881. And if we square 29, we get, 841. We get 841. So what we find is this indeed is a right triangle. And if it is a right triangle, that means we have this is a right angle, which tells us that yes, LM is tangent to circle K. We can use the Pythagorean theorem to come to that conclusion if we don't know that. Now this other problem, it gives a great example of, it says that it is tangent. So if it is tangent, this is a right angle. It's asking us to find the radius. Well, we still can use the Pythagorean theorem here, because x is a leg, x squared plus 24 squared equals the hypotenuse squared, which is going to be x plus 16, which kind of makes this look like it's going to be a little bit more difficult than it really is. But let's go ahead and see if we can figure it out. So we have x squared plus 576 equals, when I FOIL that out, I get x squared plus 32x plus 256. Well, I end up canceling out, my x squareds cancel out when I subtract them, and I can subtract 256 from both sides, leaving me with 320 equals 32x. Divide by 32, and that's pretty easy. We should be able to do that in our head, and x equals 10. It says to find the value of x, so that's my answer. So another example of how we can use the Pythagorean theorem to find missing lengths, in this case the radius of a circle. Alright, let's look down at this starred statement. It says that if two segments from the same exterior point are tangent to a circle, then they are congruent. And what this means is, do you see this drawing, how this, well, it says that AC and BC are tangent. This segment is tangent to this segment. Now they come from the same point, and they're tangent to the same circle, therefore these two segments are congruent. So if we're trying to find the value of x, all we have to do is set 4x minus 3 equal to 3x plus 2. Solve for x and we find that x equals 5, which is what we're looking for, so no need to plug it in. Continue with the notes. Before we look at this section, just want to mention, you'll recall that inscribed angle is when the vertex of our angle is on the circle. We talked yesterday about a quadrilateral that is inscribed, having opposite angles that were supplementary. Well, today we're talking about, a polygon that is circumscribed. If it is circumscribed, every side of the polygon is tangent to the circle that is inside of it. So look at this first example right here. We have a triangle. Notice that all three sides of the triangle intersect that circle at one point. So yes, that is an example of a circumscribed polygon, or a polygon that is circumscribed about a circle. The next example, yes, even though it's not a regular polygon, every side of that polygon is tangent to the circle. Another example. The next one, yes, every side is. Notice this one. The only side that it does intersect at one point looks to be this one. Other than that, we have 2 points here, 2 points here, so that would be no. That is not an example of a polygon that is circumscribed. This side of the polygon does not even touch the circle, and remember it says that every side is tangent to the circle, so that's another no. And then this one's easy, because none of the sides of the polygon are tangent to the circle. Okay, moving on. Let me move this up. Erase that. So here we have a word problem. The round cookies are marketed in a triangular package to pique the consumer's interest. If triangle QRS is circumscribed about circle T, find the perimeter of triangle QRS. So we need to find all the side lengths. Now recall that what we said before. Let me zoom in on this. This might be more helpful to do. Recall that we said if we have, this is tangent, and this is tangent, and they're coming from the same point, therefore this segment is congruent to this segment. So if this segment is 10, this segment is also 10. This segment is congruent to this segment. So if we have 2 here, this side is also 2. Now if the whole thing is 8, I have 2 here, the bottom side has to be 6. And again, that's going to be congruent to that segment, which is also going to be 6. So we have this segment, which is 8, this segment, which is 16, and this segment, which is 12. The perimeter is all those added up, so 16 plus 12 plus 8 equals 36. Our units are centimeters. That's the perimeter of the triangle.